All right, so the relationship between milliampere and time mass. Okay, state the reciprocity law. Okay, we'll talk about it. Calculate mass when given a MA and exposure time. You should know that right now. Okay. Explain the relationship between KVP and X-ray emission. State the 15% rule, which we talked about it already in different sections. Calculate the new KVP value needed to maintain receptor exposure. Okay, and changes using 15% rule. Explain the relationship between distance and X-ray emission. Okay, state the inverse square law, which I've been giving it to you. So, a lot of what we're going to do, I've been hinting at you before. Calculate X-ray emission when distances change. Okay. Calculate mass needed to maintain receptor exposure and radiographic film density when changes are made in distance using exposure density maintenance formula. Prime exposure factors, kilovoltage peak. All right, milliamperes, exposure time, that will give you mass, distance, and so these are three exposure factors, okay? Three main things. A lot of times we think of KVP and we think of MA, mass, but we forget distance. Distance is just as important, okay? If you think about the inverse square law, it will have a great effect on the end result, on your radiograph, okay? And so it's important, and a lot of times we don't think about it because we use the standard distances, 40 and 72. But if you're doing porables, then it changes. Okay, you have to keep that in mind. You try to maintain it at 40 and 72, but how many of you do chest x-rays, porable chest x-rays at 72? Very few. Isn't that what you do in your x-ray room? Yeah. So how come we don't do that when you're doing porables?
What's available?
Huh?
What's like available, the space?
The space that you have, yeah. But ideally you want to do it also at 72. Okay. Remember, well, we'll see it. We'll reinforce it here. And so we don't think about it, but it's something that it needs to be in your mind that if you change your distance, your technical factors are going to change. Okay. All right. Take control. Take control of this factor. This is what you have control of. I mean, we don't pick patients, we don't pick x-ray rooms, we don't pick the brand of x-ray equipment. So pretty much what we are left with is your technical factors, okay? And even, you know, and we have AECs and all of that, okay? That's fine, you can use it, but I encourage you to use your technical factors. Okay? If you know technical factors, okay, if you learn technical factors, then everything will be really easy. When you're using your photo timer and your AEC, it will make more sense to you. Okay. All right, your job is to know how to combine these factors to produce high quality radiographs. And I'm not saying, when I say high quality, I'm not saying the most beautiful radiographs. I'm saying high quality radiographs. Radiographs that are of diagnostic quality. Make sense? Okay, so that's our goal, to have a diagnostic quality x-rays with the least amount of radiation. That's our job. Okay. All right, quantity and quality. Quantity of the beam is also refers to the intensity of the beam. We'll look at that before, right? Oh yeah, it should be engraved in your souls now. Right? Measure in Rankin, right? Yes? Yeah, right? Okay, and Rankin, by the way, how is it measured? Remember I asked you to memorize that value?
Value or what it is?
Yeah, no value. Let's start with the value. Now we measure Rankin. I'll help you. It's measuring air, right?
Air.
And what was that value? You're gonna need it for Friday. All right, let's move on.
Where is it?
No, I'm not gonna tell you. No, why is it? Just like my kids. What is it? Go look it up yourself. Yeah. Yeah, I'm doing homework. And he goes, what's the answer, Daddy? Can we just get to the answer?
I know you do.
Yeah.
No, you didn't.
Yeah. All right. right, quality refers to the beam penetrability. All right, different things, right? So quality refers to the beam penetrability. And I've been talking about KVP and penetrate, right? So when you increase KVP, you're increasing the quality of the beam. Okay? How many of the photons will penetrate the anatomy? It doesn't matter how many you have, but if they don't have enough energy, they are not going to make it out. Okay? They don't make it out. Remember the other day that very first lab we did, and we were measuring, or was it the second? I can't remember. We were measuring exit dose.
No.
Very few, right? If we had increased, we can increase mass 3 times. It will be the same percentage. The same percentage. It will not increase. That exit dose will not increase. It will only increase if we increase KVP, which increases the penetrability. Then that percentage will go up. That make sense? Okay? All right. Quality is numerically. We're going to think of quality numerically will be represented by the half value layer. And I know you guys studied the half value layer with Martin last semester. But it has what the way you define the half value layer has to do with the amount of material needed or required to cut, okay, the amount in half. Yes? Okay. So that's how. So it gives you, so we can have a sense of quality. So we can have a sense of quality. We use this. Okay. Otherwise, it just doesn't make sense. Because if you just say, well, my quality goes up if I increase KVP, but how much did it go up? See, you cannot quantify it. And so to be able for us to be able to quantify it, to have a numerical value, we have to use it, we think in terms of the half value layer. However, the half value layer, if you look at the definition of the half value layer, it's saying is the amount of material to cut the intensity by half. So even though you're looking at quality, you're measuring in terms of quantity. Make sense?
And intensity equals quantity?
No.
No.
Okay. But see, look at the definition of the half value layer. Okay? Think about it. Think about it in your own head. Is the amount of material, whatever material that is, say is lead. Let's think of lead. Is the amount of lead to cut the quantity in half. And that's what we're using to numerically represent quality, I'm sorry. See that? See that's
But you said intensity by half, and you said quantity by half.
well,
But
what is it?
you're not including the quantity and intensity? Okay,
No.
so it's a little confusing.
It's confusing. That's what I'm trying to clarify. That if you look at the definition, and if you don't remember in your head, read it. Okay. I'll say it again. Don't write it down. Just pay attention. The half value layer is the amount of material, whatever material that is. Sheet rock, wood, concrete, lead, aluminum, is the amount of whatever material is needed to cut the quantity or intensity by half. Isn't that what it is? Isn't that the definition of the half value layer?
Quantity, yes, that's the amount.
Yeah. It
But
was
it
what's
also-
another term that we use for quantity?
Amount.
Intensity. Intensity. Remember, intensity and quantity, and quantity are the same in diagnostic radiography, right? Yes?
Yes.
They are. It's the same thing. You're talking intensity and quantity are the same. All right? So, let me go back to the definition. So we're using numerically, to numerically represent quality, we're using the half value layer. However, the half value layer is a measurement of quantity. Quantity. See? Interesting. But otherwise, if you keep it just with quality, it just doesn't make sense. Numerically. Okay? If it doesn't click yet, it hopefully it will. If not, just memorize it. Memorize it. Yeah. All right. What do you think? Okay, let me ask you this. What do you think the health value layer is important? Let's see if you understand.
When you're making a barrier filter.
Why will that be filtration, okay, and barriers? Why? And that's for both of you. Why will that be important?
Well, when we're shielding the patient, how much lead is needed to reduce the quantity, the amount of X-rays going through.
Okay. See what you said is the quantity.
Yeah.
However, will that depend on the KVP?
No. Yes.
Yes, because the higher isn't it the higher the KVP, the more penetrability you have?
Yeah.
But did you see what you're doing? That's
Yeah.
what you're doing it in terms of quantity, but is to measure the energy. How about filtration?
You want to see how it's able to filter out how many photons. So you have to use that to see how much it's cutting down from it, from the
Exactly.
original amount.
Yeah, exactly. And so what physicists will do, you know, they will measure. Filtration, for example, is measured, but is measured with different KVPs. Okay? You will measure with different KVPs because the Hall value layer will change.
Yeah.
Okay, you have a set value layer, but that value layer, you can make it flip. You can, when I say flip, you can make it, say for example, if I have a quantity of radiographs, I don't know, say 5 Rankins, that's what we have, 5 Rankins. We want to cut it in half. Okay, what will that be? 2.5, right? So we want to cut down, and so we're going to use the amount of material required to get that intensity to 2.5. Make sense? Now, and KVP set at 80, which is typically where you measure it. But how about if we go to 120? 3.2 is not going to do it. You're going to need more. 3.2 is the standard. Typically at 80, 3.2 lead equivalent is what it will cut your intensity by half at 80 kVp. But if you're using something else, if you're using 100, 120, it will be more. Okay. Well, go ahead.
Is it because for the intensity it's the amount of photons and that's why you can measure it? You can't really measure the
Exactly. It's difficult to measure energy.
Yeah.
Very difficult. But amount, you can measure it. You can just put material and then you put an ion chamber, just like the little ion chambers we used the other day, the little square things with the round thing in the middle. Yeah. Okay. Mm-hmm.
You said 3.2, was it a lead equivalent or aluminum? For 80, you said 80 kVp.
3.2 aluminum. I'm sorry, aluminum equivalent. Yeah, 3.2 lead. We've not allowed anything to go through.
Okay. Double checking.
Well, everything. Aluminum. Yeah. All right. Are we good so far? Is that making sense? Okay, good. Let's move on. Factors affecting X-ray emission. So let's look at the easy one first. Okay. So we're gonna look at quantity. Okay. And so we're gonna be looking at quantity, quality, and distance. Okay. And all related. So factors affecting the X-ray emission. Quantitative. Okay, and that has to do with the milliamperes, so it has to do with MA, kilovoltage, distance, and filtration. All four play an important role in the quantity of X-rays that are being emitted. Are you following me? All of them play a role. Okay. Now, not all of them play a role in the same way. Okay. So, for example, milliamperes and time will be directly proportional. Okay. Inversely proportional is square, okay? Distance, the inverse of square law. Filtration, I'll explain that in a second. Okay? Are you following me? All right, good. All right, qualitative. Okay, this has to do with the energy, and that only two. Okay, kilovoltage and filtration. That's it. Kilovoltage and filtration, nothing else. So this one, quantity has 4, quality has 2. Okay, so let's start with the MA, the milliamperes. Okay, determines beam quantity or intensity. Okay, you can put instead of or, you can put equal intensity. Okay, or something. But in diagnostic radiography, quantity and intensity are related. Okay, change the EMA station on equipment, and then you will change the current delivered to the filament. All right, so now we're going to go back to that very first section, section 1, where we look at that. You know, when you look at the, when you look inside the X-ray equipment, right? And what happens? Remember, in line coming in, you have a auto transformer, and from the auto transformer, you send a signal to the step-up transformer, and then another signal to the step-down transformer, right? And from the step-down transformer, what do? It goes to the filament, right? So that's what I'm talking about. So you change the current delivered to the filament. All right, good. Change current to filament. Okay, change how many electrons are released through thermionic emission. You guys remember that? What is thermionic emission? Gary, what is thermionic emission?
Basically, you heat up the filament, and while there's current running through it, and then that releases electrons.
Good, good. So that's thermionic emission, right? Okay, so that, when you're changing your MA station, really what you're doing is you're changing the current. Not only the current that is going through the filament, but it also changes the current that you're going to have between the cathode and the anode. Everybody?
Can I see that
Good.
again? Just
Which,
kidding.
which part?
So
Which part? Go ahead.
changes the current of the filament, which in turn changes the current between cathode and anode.
Remember, if you remember from, just to clarify. Okay, so you have, I know it was only 2 months ago.
So long ago.
So you have the filament, right? And it's going to the step-down transformer, right? And it's running a current here. This current is measuring what?
Measuring what?
Is measuring what? Milliamps or amps?
Yeah.
I'll make it easier for you. Milliamps or amps? Amps. Okay, this is measuring amps. All right, this is in amps. Okay. However, remember there is another part of the circuit that is not connected to this circuit that is here somewhere. Okay. Okay, and this one is measured in milliamps. You guys remember that? The flow of electrons. How do we define the flow of electrons? What is it that I'm saying? Current, exactly. So the current here, not here, but here, is measuring milliamps, and this current here within the filament is measuring amps. Right? Okay. What will happen if we were to measure, if our current is measuring milliamps here? Here, in the filament. What will happen? Nothing. No thermionic emission. The whole reason you have amps here is you can heat up the filament. And then you can have thermionic emission. Okay? However, your switch in your panel, when you're changing MA, okay, you're not really changing. Have you seen a switch on your panel? Have you seen a switch for amps? No. So it's the same switch when you're changing, depending on the milliamps that you have, is also increasing or decreasing the amperage here. Make sense what I'm saying? So, if I'm here, right, I'm here in this panel, and I'm trying, oh, I want high thermionic emission, I want to increase the current through the filament. There's no amps here. There's no amps. I mean, you can look everywhere. There's no amps. All I have here, all I have is a choice for milliamps. And so, it is one switch that will change. This is mainly what you're changing. However, changes here affect the amperage that you're using here. Okay? Yes?
Yeah.
Okay, good. So, that's what I'm saying here. Change the MA station on equipment, like I just showed you back there. Change the MA station, and the change current delivered to the filament will also change. So this will also change. Even though I'm changing this, it will also adjust it depending on how much I will need here. The amperage will go up or down. Okay? Just to check. What's the average amperage that we have here? Shall I tell you?
Yes.
Nah. Look it up. It's very low. The amperage, it has to be low. I mean low in terms of amperage, not milliamps. Right? All right. So the change current delivered to the filament. Have an answer? No. Stretch.
1 to 5,
I hope not.
like 1 to 5 amps.
There you go. Good. Thank you.
1 to 5?
1 to 5.
Rods.
1 to 5 amps.
All right. All right, so change current filament, which will change how many electrons are released through thermionic emission, right? Okay, so depending on how hot this thing gets, it will release more or less electrons, okay? And then you have this cloud here, right? And not until you make that exposure, until you go beep, okay, until you make the exposure is when you measure the current in milliamps, going from here to here. All these electrons that you have here will flow to the cathode, to the anode. Okay, so that's what we're doing there. So current, units of current is the amperage. Okay, 1 amp is equal to 1 coulomb. Okay, approximately 1 coulomb of electric charge flowing in 1 second within a conductor. So 1 amp, 1 coulomb per second. Okay, which is equal. Take a look. You've seen this number before, and I'm bringing it back to you. Okay, 6.3 times 10 to the 18 electrons per second. Lots of them. Right? Lots of electrons in 1 amp. Okay, 1 milliamp, which is more of what we use. You're going to have, if it is milliamp, just cut 3 there, 15. Okay? 10 to the 15 electrons per second in 1 milliamp. So there is a lot of electrons flowing, lots of them. Like 10 to the 16 is more common. Okay, lots of them. All right, now tube current, direct relationship to beam intensity. Okay, so change 200 to 300, that's going to change 50%. If you go from 200 to 400, that will change 100%. It's directly related. Okay, very simple. So 50% increase in the number of electrons emitted from the filament is a 50% increase in the number of photons that you have. Simple as that. Okay, why? Because what you're doing is you're changing the number of electrons flowing from here to here. When you're going from, say, 100 MA to 200 MA, you're doubling the number of electrons. Okay? You double the number of electrons that you have from here to here. Okay? And if you have the double number of electrons, that means that you're going to have double the number of interactions. And if you have the double number of interactions, that's the double number of photons. So it's directly proportional. That's what I'm saying there. Okay. Right. Now, controls the time. The time is what controls the duration of the exposure. How long are you going to allow the electrons to flow? Okay? And so it's directly proportional to the intensity again. Okay? You double your time, you're going to have double the amount of photons. Cut the time in half, you will cut the amount of electrons in half. Make sense? Make sense?
Yeah.
You need to be excited about things. Yeah. Short exposure times are useful in reducing motion area effect. Yeah, that's an interesting. All right. Older equipment express times in fraction. Okay. Good thing. You don't have to deal with that. So you don't have to be doing divisions in your head. It's all done in decimals for you. Or they already give you the mass. Okay. It's even easier like that. Those two. Okay. Newer equipment typically express times in milliseconds. There's something to be aware of. Recall that exposure is measured in seconds. Okay. All right. When you're doing exposures, remember that's always going to go back to seconds. Did you see our little ion chamber? What was it measuring in? Well, bit rate. Rangens per minute or rangens per second, either way. Okay, so it's always, so exposure is always measured in seconds, not milliseconds. All right, so a few more things. MA times time will give you mass. Woo. Yeah. All right. So if you multiply your seconds, okay, not milliseconds, because you will end up with some crazy math. When you multiply your seconds, okay, multiply it by MA, it gives you your mass. Does everybody knows how to do that? Oh, okay. All right. Controls. Okay, so mass controls quantity, radiographic density, patient dose. And when I said patient dose, you can also say exposure. Exposure to what? To your receptor. Okay? Why am I saying that? Because with DR or CR systems, we don't use radiographic density anymore. We use S numbers, exposure index. Remember those? Okay, and so it's difficult to see it. But the exposure to the plate, when you double mass, the exposure to the plate will double. Okay, just like density.
Okay, so that's the exposure.
All right? But I have to talk about density because you're going to be tested on it. Okay? If it's up to me, I won't because you don't use film. So far, so good? All right, good. Okay, a few more things. All right, mass reciprocity. The same radiographic film density will come from different MA and time selections, provided that mass totals are equal. Okay, does it make sense?
Yeah.
What this is saying is that it doesn't matter what combination you use of MA and time, as long as the end result is the same mass, you should have the same exposure. That's called reciprocity. Okay? So, same radiographic density will result from a different MA and time selection, provided that the mass total is equal. Once, you know, if the end result is equal, you don't care if you use the 25 MA station in whatever time and the 500 MA station, as long as the mass end result is the same, okay, you should have the same exposure. Okay? Now, it doesn't always work that way, okay? because X-ray equipment is not perfect. Okay? Even though you thought it was perfect, it's not. It's not perfect. All right, so it might not work. So now take a look here. In this case, all right, I used to have, I don't have it anymore. Yes. Crazy. There. All right, so these three radiographs where, yeah, this one looks a little darker. Yeah, kind of. Yeah. But we use the same mass, total mass, with different combinations of MA stations with the same mass. They kind of look, so this one looks darker, obviously. Okay, but they should all, they should look the same. Okay. That's what reciprocity is saying. We're gonna do a lab. We're gonna make a, I'm sorry, some of you are really closing your eyes. Come on, be awake. Some of that. Let's just stop here. Let's just stop here. You're gonna fall. Yeah, go fall